So today I would like to speak about our implementation of a super resolution device, which in particular is operates in the time and frequency domain, which is less standard than typical super resolution protocols that are known in classical or quantum imaging. So I come from the Center for Quantum Optical Technologies at the University of Warsaw, and this work is part of our international research agenda, as well as of a grant dedicated to the super resolution protocols from the Office of Naval Research. So I have myself worked on super resolution since already a few years. And in particular, we have presented a protocol in which we can achieve super resolution in distinguishing 2 point sources using Hong-Mandel interference. And more recently, I've been also involved as a postdoc at the University of Copenhagen, working on entanglement and quantum metrology in other terms. However, in Warsaw now, we are concentrating on trying to beat the Rayleigh limit. So the famous paper of Rayleigh is well known in the imaging community, as it sets the fundamental limit for distinguishing 2 close-by sources given by the wavelength and the numerical aperture of our device. However, this is actually for 2 dimensions, but interestingly, in the original consideration by the author, he has actually considered the resolution limit in terms of a spectroscope, so a spectrometer, like the modern version that you can see here. So in a spectrometer, the resolution is going to be limited by the slit, and in fact it is just as in the imaging 2D imaging case, it is an imaging system, and similar laws will govern the spectral resolution of the device. So how do we treat this Rayleigh limit in more modern informational terms? So this has been known for some time, that actually we can formulate it in terms of information theory. So in particular, we want to consider how do we distinguish, how do we estimate the epsilon parameter, which is the shift parameter of the 2 close-by sources, and we will assume that those sources are lying really close to each other, such that they almost overlap and that we cannot distinguish them. So we operate well, by default, we operate well below the conventional Rayleigh limit. So in this case, we can calculate what is the precision in estimating, or rather what is the information per any photon registered by a camera device in the context of this imaging system. So as it turns out, we can use the Fisher information theory and then use the Kramer-Rao lower bound to estimate the precision per photon. And it turns out that it falls very rapidly for small epsilons, and in particular in this convention here, it will look like epsilon squared over 8. So what's really important is the epsilon squared. So for low separations, we have almost no information about precision, and this is called this is often termed by the Rayleigh curves. So now we see that, for example, here for low separations, those are the plots from one of the works that have considered this the Rayleigh limit in this context theoretically, but the main contribution of the quantum information science for this has been to notice that, in fact, this epsilon squared scaling is not fundamental. So it turns out that if you consider the quantum Fisher information, which is the Fisher information optimized over all possible measurements of the optical field, then the information or the possible precision of estimating the separation is actually constant. So it doesn't fall for small separations. Furthermore, you can also still estimate the centroid of this composite source quite well. So this has been noticed by Mankei Zhang, and since then many proposals have been developed on how to actually implement this optimized quantum inspired measurement. So all those proposals, perhaps all of them really depend on noticing that a shifted source in terms of, for example, Gaussian transfer function is actually just an unshifted source plus a small contribution of a Hermite Gauss, or if it's shifted the other way, it's minus a small contribution of a Hermite Gauss. So we really want to, so now we have some signal. This Hermite Gauss will have, will carry a signal that is proportional to this exact separation that we want to estimate. So the idea is, how do we filter out only this Hermite Gauss contribution? And it is also important to notice that it indeed still works for incoherent sources. So generally, we can say that we want some spatial mode demultiplexing, that we sort the optical field into spatial modes and we'll detect only the Hermite Gauss. It can be in general implemented, but one interesting idea that we will look in the temporal domain in our work is to actually invert the image and then interfere it with itself. This projects the optical field into an even and odd mode, which indeed is for small separations the projection onto the Hermite Gauss. So it turns out that this protocol will achieve a Fisher information scaling that is almost optimal, and in particular it's constant minus a small factor, so it's really for small separations, which is the regime we are interested in, the super resolution regime. Then we will have a scaling equal to the quantum Fisher information. So where do we really want to distinguish two close lying spectral lines, because this is something that we want to target here. So that turns out to happen in many scenarios, and spectroscopy with very broadband light will be certainly one of them. But here we are targeting, really we want to achieve super resolution, but also for actually very high resolution. So at even at single kilohertz of the optical frequency, the level of single kilohertz. So systems like that involve single ions, so we could try to distinguish emission lines from single ions to, for example, measure gradients of various fields. The same can be said about cold atoms, as well as signals transduced from lower frequency domains, such as, for example, in optomechanics, one can imagine close-lying mechanical modes of a membrane that I have worked myself here with, and it is interesting to try to distinguish how far those various modes will be separated. So our system is actually called atoms, but we will not be trying to detect emission from cold atoms and try to do spectroscopy with that, but we will actually implement the spectroscopic device in the cold atom system. So the general idea that I want to stress here is the following. We are looking at the spectroscopy as a form of temporal imaging. So we start with some field in the temporal domain, and we want to make a Fourier transform. And if you want to make a Fourier transform in the spatial domain, well, you place a lens and two distances equal to the focal length, and the field at the output, I mean, still detected in time, but will effectively be a Fourier transform of the field and the input. So how do we realize such a transformation in the time domain? And well, we can already see that this indeed is the spectrum of this of those two pulses, because well, we see them interfere. So this is exactly what we want to achieve. This temporal imaging is a field mostly well known in the ultrafast domain, in the ultrafast community, where different elements such as a lens or propagation known from spatial optics are considered in the time frequency domain. So to realize a temporal lens, we want a phase that changes in time, that is realized, for example, by an electro-optic phase modulator or by some wave mixing processes. And if we want to have propagation, then we want a quadratic phase in terms of frequency, as it is in the case of spatial domain. We have a quadratic phase as a function of the transverse wave vector. So here we want a quadratic phase as a function of frequency. And this is known as the group delay dispersion. So we, for example, make a dispersive delay line, or we just put a highly dispersive or just a very long piece of fiber to have a lot of dispersion. But those techniques will not really work in the ultra-narrowband domain, mostly because it is just very, very hard to make so much dispersion without inducing a horrible, horrible loss. The phase modulation, which is often a challenge in the ultrafast domain, is actually going to be easy in the narrowband domain. So our system we will implement those operations in the via a light atom interface. So some of them will be implemented in atoms. And our interface is based on a three-level system where we input the signal field to pre-pumped atoms. And with using a control field, we can map the signal into the atomic coherence, which is stored as a spin wave in the ground state of the atomic ensemble. And then we can apply another pulse of the control field to retrieve the spin wave. Furthermore, we place our atoms in a gradient magnetic field, such that when the signal field is input, different frequencies of the signal will be mapped into different z positions along the very long atomic cloud. This can be modeled as a set of Maxwell block equations. And in fact, this protocol has been realized before in different atomic systems. And it has been termed the gradient echo memory. Now we add one more touch to the gradient echo memory, which is that we can also control the phase a bit more than just with the gradient of a magnetic field, but we use a further tuned AC Stark beam to eliminate the atoms from the side, so that we can program this phase shift in the particular in the z direction as a function of the position. And in the past, we have already demonstrated several protocols with that. But here again, we want to do this far-field temporal imaging, and we'll actually do it a little bit differently. It turns out that the same transformation, as can be proved with ABCD matrices, can be done just by two lenses and one propagation. And that's going to be nice because, as I said, in the narrowband regime, it's easier to make a lens than the spectral dispersion. So the lens is realized very easily by actually modulating the control field in frequency. So we make a chirp in the control field, which translates via atoms into the signal, which effectively makes both the input and the output temporal lens. Now, between input and output, the different frequencies of light are mapped into the different z directions along the ensemble. So it is quite easy to add the spectral phase with our AC Stark shift. So we illuminate the ensemble from the side, we program the phase to change quadratically with the Z parameter along the atomic ensemble, and we get a lot of spectral dispersion compared to what can be seen in for example fibers. That actually the amount of spectral dispersion that we make would require very, very long pieces of fiber that would lead to thousands of dBs of loss, or if not more. So the language that we also like to understand this with is the Wigner function. So we can, so this is not the typical Wigner function that we use for quadratures of light. Rather, this is the so-called chronocyclic Wigner function, which is just a Wigner transformation of the slowly varying optical amplitude. That effectively makes a spectrogram, which also preserves coherence, which, as with this definition, is the Wigner function. So we can understand different transformations of the Wigner function. So I will actually just show them on a picture. For example, for those pulses, we can calculate this spectral, this chronocyclic Wigner function, and it looks like in the cut state node from quantum optics, and subsequent transformations will lead to rotations in the T omega space, which is mapped in the atomic ensemble into KZZ space of spin waves. And we can make the full rotation, which in fact makes a Fourier transform and allows us to observe the spectrum. And in our experiment, we've been able to really observe the operation of this Fourier transform. We can put two pulses and get a train, or start with a train and get the two pulses back. So going back to the two incoherent sources, well, if we lose coherence, then the Wigner function loses the fringes, but it doesn't permit our device from operation. And what we can get is that as we increase the separation of two simulated spectral lines, then we see that at the output of this exact device, we get two peaks, which correspond to two spectral lines. And the separation, clearly for small separations, is very hard to even estimate this separation. However, we can make a device that will filter out the Hermite-Gauss component of the optical field in the spectral domain. So we will make an analog of this device, which inverts the optical field in the spatial domain and interferes it with itself. So what we'll actually do is that we cut the pulse in half. That is effectively done with a modulator, and then we reverse the time, which is actually equivalent to reversing the frequency in one of the arms of this virtual interferometer. At the output, we pretty much get two ports of this beam splitter. And now, as we increase the separation, we get a lot of sensitivity to small separations in the antisymmetric port, or the port that corresponds to this Hermite-Gauss combination. However, the entire protocol is very importantly realized inside the atomic ensemble. So, how that happens is that we map the signal to the quantum memory using a control, changing the tuning of the control field. So it will actually switch the tuning chirp as the pulse is stored. And this switching point corresponds to this splitting point in the previous slide. So this implements this device. However, the two parts of the pulse actually land in the same quantum memory. However, they land in the different space, in the different place of the Wigner space. So one lands as a rising slope and the other as a falling slope. Now we will have the internal coherence between different parts of the pulse if we just store a Gaussian one. Now, very importantly, those two parts have a different phase with respect to each other, which is encoded in these fringes. So even though they look very similar, if we input a symmetric or perfectly anti-symmetric pulse, then at the output they will have they will exit in different ports. So how that happens is that once this is stored in the memory, and this is the Wigner function in terms of this is the position along the ensemble, and this is the wave vector of the spin wave stored in the ensemble. So now we make a beam splitter between this part and this part. So we want to have a grating that will just mix different components with a different wave vector along the ensemble. So that is the AC star grating that we illuminate the ensemble with, which makes which effectively leads to spin wave diffraction and interference. So I can say this is a grating with a changing periodicity. So it must have a higher periodicity here because it's a larger wave vector, and lower periodicity here because it's a lower wave vector. So next we read out one port, then we put in actually a different grating which reverses the process, and we can observe the other port. So I referred to more details to our archive paper about that, but the important part is that we indeed obtain the two ports. Now, I don't want to go too much details in the modeling. However, importantly, we even though we do lose a bit of the signal at the very input, which is related to the shape of the atomic ensemble, we actually can prove that, and more of that is in the methods part of our preprint, and we can show that we still achieve a super resolved sensitivity, and this is also thanks to a very high visibility of this interference, as it is all implemented within a single atomic ensemble. So we get more than 99% visibility. Finally, indeed, we see that very little information is contained in this part that we lose, which is again related to the shape of the atomic ensemble. So slowly going to the conclusions and comparison of the two schemes, we can estimate the separation given the number of photons that we register in one and the other port. And we see that the variance of this estimator, the estimator for epsilon, the separation, is much lower in our pulse division time axis inversion protocol than the typical quantum memory temporal imaging protocol presented before. So, and the precision actually exceeds for small epsilons the conventional protocol precision more than 20 times. So that means that to get the same precision in estimating the estimation, we need to use 20 times less photons, which in particular may translate to the 20 times less measurement time. Now we can define it indeed exactly like that, the super resolution parameter. And this is the very important part to mention, that the singling, the filtering of the of the Hermite-Gauss part has also been realized in a nonlinear crystal, which is called the quantum pulse gate protocol. However, in our protocol, we achieve a very similar performance, yet at a vastly different frequency scale, which also translates to a much different spectral resolution, much higher spectral resolution, the kilohertz level rather than a terahertz level. So finally, one can also ask whether a homodyne measurement would be better in this case, because in homodyning you just observe the two lines as a bit node with a reference laser. We are now as it turns out, if you just do a power spectrum, then it will never be better due to shot noise. And in general, if you have a weak signal at the single photon level, the shot noise will always spoil the result. But you can get some spectral resolution out of it, spectral super resolution out of it, and this is what we are also intensively working on with Konrad Banaszek and the Fiori team, and their paper has been published, which is about the same thing, but in the spatial domain, but it actually presents the very same idea. So I would like to thank the collaborators who worked with me on the super resolution projects, as well as the previous normal resolution projects, and thank you for your attention.